Imagine the North Atlantic in 1942, icy waters, waves that swallowed ships whole, and beneath the dark surface, deadly shadows lurked every movement. German submarines, known as U-boats, turned that ocean into a floating graveyard. Hundreds of merchant ships laden with vital supplies for Britain sank every week. Food, fuel, weapons, everything sank before even reaching its destination. The situation was desperate. The Allies were losing the Battle of the Atlantic, and without winning this invisible war beneath the waves, the entire fight against the Axis powers might be lost. But in this bleak landscape, an ordinary man, an electrician, working in the dark holds of ships, had an idea so simple, so seemingly absurd, that his superiors laughed when he first proposed it. This crazy idea would completely change the course of naval warfare and save thousands of lives. This is the true story of how a brilliant trick, born from the mind of an anonymous technician, defeated the most feared technology on the seas. Before we continue with this incredible story, if you're enjoying this content, subscribe to the channel and leave a comment about the time you watched this video. Now let's get to the story. To understand the genius of this solution, we must first grasp the terror that U-boats represented. When the war began in 1939, the German Navy possessed only 57 operational submarines. It seemed small, but Admiral Karl Dönitz, commander of the submarine fleet, had a devastating strategy. He called it Rudeltaktik, which in English means pack tactics. The submarines didn't attack alone. They communicated with each other by radio, coordinated positions, and attacked in groups, especially at night, when they were virtually impossible to see on the surface. A typical Allied convoy had between 30 and 60 merchant ships sailing together, protected by just a few destroyers and corvettes. When the pack attacked, it was absolute chaos. Explosions lit up the night, ships split in half, burning oil spread across the water, and the sailors' screams were lost in the icy wind. Between 1940 and January 1943, U-boats sank more than 1,000 Allied ships. This represents about 5 million tons of cargo on the ocean floor. Great Britain depended on these imports for survival. Without them, the population would starve, factories would shut down, and resistance to the Nazi occupation of Europe would be impossible. British Prime Minister Winston Churchill would later write that the only thing that truly frightened him throughout the war was the threat of U-boats. The Allies tried several countermeasures. They created the convoy system where merchant ships traveled together under naval protection. They developed sonar, which used sound waves to detect submerged submarines. They introduced depth charges, bombs that exploded underwater and could destroy a submarine even without hitting it directly. Patrol planes began flying over shipping lanes, forcing U-boats to dive and slow down. All these measures helped, but they weren't enough. The Germans always seemed to know where the convoys were, even when routes were secretly altered, even when the ships maintained absolute radio silence. The submarines appeared in the right place at the right time. It was as if the Allies were sending out invitations to their own funerals. And in a sense, they were. The problem was invisible, silent, and deadly. It was related to something no one imagined could be tracked: the magnetic field of the ships themselves. Every metal ship, especially large cargo ships and warships, creates distortions in the Earth's natural magnetic field. It's like an invisible signature that the ship carries wherever it goes. During the early years of the war, no one paid much attention to this, but the Germans had brilliant scientists working on their weapons development programs. They discovered they could detect these magnetic anomalies at considerable distances. They developed magnetic detectors sensitive enough to detect the presence of ships long before any sonar or lookout could detect a submarine. Even more dangerous, they created magnetic mines. These diabolical weapons lay motionless on the seabed, waiting. When a ship passed overhead and its magnetic signature was detected, the mine exploded. There was no way to see these mines. There was no way to deactivate them with conventional methods. They turned ports and strategic sea lanes into deadly minefields. Hundreds of ships were destroyed in this manner, many of them still in waters considered safe. Close to Allied bases, the situation was so dire that in 1939, right at the start of the war, The British Admiralty formed special teams of scientists and engineers to study the problem. They ran tests, measured magnetic fields, and studied different types of ships. They discovered that the problem was complex. It wasn't just the metal of the hull that created the magnetic signature. It was also the magnetization the ship acquired during its construction. When steel plates are cut, welded, and shaped, especially in shipyards located in the northern hemisphere, they become magnetized by the influence of the Earth's magnetic field. Over time and with use, this magnetization changes. The ship essentially becomes a giant floating magnet, and the older the ship, the stronger and more distorted its magnetic signature. Scientists proposed several solutions. One was to build ships with special non-magnetic alloys, but this was too expensive and time-consuming. Another was to periodically demagnetize ships using massive equipment installed in ports, but this was also impractical for the number of ships requiring protection. That's when our electrician entered the picture. His name was Charles WWII, though other technicians and engineers were also working on parallel solutions. WWII wasn't a famous scientist. He was a practical man who understood electrical circuits, cables, currents, and magnetic fields the way a technician does, not just theoretically, but by knowing how things actually work in the real world, with all their imperfections and surprises. He was serving in the Royal Navy as a lieutenant commander, working in the Research and Development Department. He spent his days in the holds of ships, measuring magnetic fields, trying to find patterns, searching for a solution that would work. And it was during one of these routine inspections, covered in grease, sweating in the heat of the engines, that he had his crazy idea. The idea was disconcertingly simple. If the problem was that ships had a permanent magnetic field that made them detectable, why not create an opposing magnetic field that canceled out the first? It was the same principle of noise cancellation that would later be used in modern headphones. If you have an unwanted sound wave, you create another exactly opposite wave that cancels it out. WWII thought, if I run an electric current through a cable wrapped around the ship's hull, it will create a magnetic field. If I adjust the direction and intensity of this current just right, I can make this artificial magnetic field cancel out the ship's natural magnetic field. The ship would become invisible to magnetic detectors and magnetic mines. It was that simple, or at least simple in theory. When WWII presented his idea to his superiors, the initial reaction was skeptical. One admiral reportedly said it sounded like magic, not naval engineering. Another questioned how a simple electrically charged cable could accomplish something their best scientists couldn't solve. There were also practical concerns. The ships were already in service. There wasn't time to redesign them or dry dock them for weeks. The solution needed to be fast, cheap, and effective. WWII insisted his idea met all these requirements. He requested permission to test it on a real ship. Reluctantly, his superiors agreed, likely more to prove it wouldn't work than because they believed it would succeed. The first test was conducted with a small warship. WWII and his team worked day and night. They installed a thick electrical cable around the entire perimeter of the hull, very close to the metal. This cable was then connected to a controlled power source. The idea was to pass a direct current through the cable, creating a magnetic field around the ship. But how strong should this current be? In what direction should it flow? These were questions that could only be answered through trial and error. WWII used sensitive magnetic detectors, the kind the Germans themselves used, to measure the ship's magnetic field. Then he adjusted the current in the cable little by little, measuring the result with each change. He increased the current, decreased it, reversed its direction, tried different configurations. It was tedious, meticulous work, requiring infinite patience. After days of adjustments, something extraordinary happened. The magnetic detectors stopped registering the ship's presence. At least they didn't register a signature strong enough to trigger a magnetic mine. The ship's magnetic field didn't disappear completely, but it was reduced to such low levels that it became virtually undetectable at operational distances. WWII and his team were elated, but there were still skeptics. A controlled test in calm waters was one thing. Making it work under real combat conditions, with ships rocking in storms, stressed crews, and equipment suffering from the salt spray was another entirely. The tests continued. Goodye's team installed the system, which they called degaussing, on more ships. Degaussing comes from Gauss, the unit of measurement for magnetic field, named after the German mathematician Carl Friedrich Gauss. The process of degaussing therefore literally meant removing or reducing magnetism. Each ship had its own magnetic characteristics, so each installation needed to be individually calibrated. It was like tuning a musical instrument. You can't simply use the same settings for all violins and expect them all to sound perfectly in tune. Each ship required its own precise adjustments. As more ships received the degaussing system, something remarkable began to happen. The loss rate due to magnetic mines dropped dramatically. Ships that would previously have been destroyed upon entering certain mined areas now passed through unscathed. The Germans were confused. Their magnetic mines, which had been so effective, suddenly stopped working as frequently. They didn't understand what had changed. Had the Allies discovered where the mines were planted? Had they developed some method to deactivate them remotely? The truth was much simpler, and at the same time, much more ingenious. The Allies weren't avoiding the mines. They were simply passing over them undetected. But the degaussing system had its challenges. The electrical current needed to generate the canceling magnetic field had to be continuous and stable. Any fluctuation could make the ship detectable again. This meant ships needed dedicated generators or had to divert power from other systems. On warships, which already had enormous electrical demands to power radars, radios, weapons systems, and more, this presented an additional challenge. On merchant ships, many of which had basic electrical systems, installing and maintaining the degaussing equipment was even more complicated. Marine electricians became some of the most important personnel on board. They needed to constantly monitor the system, make adjustments as needed, and ensure everything worked perfectly. There was also the problem of maintenance. The degaussing cable, exposed to salt water, corrosion, and mechanical impacts, needed to be inspected regularly. If the cable broke at any point, the entire system would fail. If the electrical insulation deteriorated, dangerous short circuits could occur. Technicians developed rigorous maintenance protocols. Before each voyage, the system was tested. During the voyage, there were periodic checks. After each voyage, especially if the ship had experienced combat or heavy weather, there were thorough inspections. It was constant work, invisible to most of the crew, but absolutely critical to the ship's survival. As 1942 turned into 1943, more and more Allied ships received degaussing systems. It wasn't just warships. Merchant ships, oil tankers, and even some fishing vessels operating in dangerous areas were equipped. The production of special degaussing cables became an industry in itself. Factories worked in continuous shifts to produce thousands of kilometers of cable. Installation teams traveled from port to port, equipping ships as quickly as possible. It was a race against time. Every ship protected was a ship that could complete another voyage, deliver another vital cargo, survive another. The Germans eventually discovered what the Allies were up to. Captured documents and prisoner interrogations revealed the existence of the degaussing system. But knowing something exists is different from being able to combat it. The Germans tried to develop more sensitive magnetic detectors, capable of detecting even the faintest magnetic signatures. They tried to create mines with more fine-tuned sensors, but it was a technological battle they were losing. As they improved their detectors, the Allies improved their degaussing systems. Furthermore, Germany was running out of resources. Producing sophisticated magnetic mines required materials and expertise that became increasingly scarce as the war progressed. Fascinating aspect of this story is how a simple technological solution had enormous strategic effects. Degaussing didn't win spectacular battles. There was no dramatic moment when an admiral announced that degaussing had turned the tide of war. Instead, it was a victory of accumulation. Every ship that didn't sink meant more supplies reaching Britain. More food meant better morale. More fuel meant fighters and bombers could fly more missions. More military equipment meant armies could be prepared for future offensives. Degaussing allowed the Allies to maintain the supply line across the Atlantic at a time when losing it could have meant losing the war. There are remarkable individual stories of ships saved by degaussing. A British tanker was sailing alone, separated from its convoy by a storm, when it unknowingly entered a German minefield known for being particularly dense. The captain and crew didn't know where they were exactly, but they knew they were in mortal danger. They heard distant explosions, signs that other, less fortunate ships had triggered mines. But their ship continued on. It passed right through the minefield, its degaussing system working perfectly, keeping its magnetic signature too low to activate the surrounding mines. When it finally emerged from that area and encountered another convoy, the captain could hardly believe their luck. Except it wasn't luck. It was engineering. Another case involved a Royal Navy destroyer chasing a U-boat near the Norwegian coast. The Germans had mined those waters heavily, and Allied commanders generally avoided operations too close to shore for that reason. But the destroyer's commander decided to take a risk. He had a newly installed degaussing system and trusted it. He chased the U-boat into shallow waters, where it would normally be suicidal to go. He forced the submarine to surface with depth charges. He sank the U-boat with cannon fire, and he returned safely without triggering a single mine. When he returned to port, other captains called him crazy. But he just smiled and said he had a secret trick. Interestingly, degaussing had applications beyond mine avoidance. It also reduced the effectiveness of magnetic torpedoes. The Germans developed torpedoes that didn't need to hit the ship directly. They passed under the hull and exploded when they detected the magnetic field of the ship above. The explosion under the ship was devastating because it hit the least protected part of the structure and could split the ship in half. But with degaussing, these magnetic torpedoes lost much of their effectiveness. Many passed directly under ships without exploding because they couldn't detect a strong enough magnetic field. The Germans eventually reverted to using ramming torpedoes, which needed to hit the target directly, reducing their chances of success. Degaussing technology also evolved during the war. The first systems were permanent, installed as part of the ship's structure. Later, more flexible systems emerged, which could be adjusted in real time depending on conditions. Engineers developed automatic controls that continuously measured the ship's magnetic field and automatically adjusted the degaussing current to compensate for changes. This was especially useful because a ship's magnetic field could change depending on its cargo, hull wear, and even the latitude at which it was sailing. A ship in the North Atlantic had different magnetic characteristics than the same ship operating in the Mediterranean. Automatic systems handled these variations without constant manual intervention. After the war, degaussing didn't disappear. Modern military vessels still use degaussing systems, albeit much more sophisticated than the original ones. The reason is that magnetic mines still exist and remain a threat. In fact, magnetic detection technology has only improved since World War II. Modern submarines can detect surface ships at great distances using magnetic anomalies. Some maritime patrol aircraft carry sensitive magnetometers that can detect submerged submarines through their magnetic signatures. The cat-and-mouse game between magnetic detection and magnetic countermeasures continues to this day. The impact of the work of WWII and other engineers like him extends beyond naval technology. They demonstrated an important principle. Sometimes the best solutions to complex problems are elegantly simple. They didn't need to redesign entire ships or develop exotic materials. All they needed was a deep understanding of the problem and clever application of basic physical principles. A cable, an electric current, and an understanding of magnetic fields were enough to neutralize one of the most feared weapons in naval warfare. This is applied genius. There's a broader lesson here about innovation in times of crisis. World War II forced technological advancements at an unprecedented pace. Radar, primitive computers, nuclear power, rockets, antibiotics, among many other technologies, were developed or accelerated by the necessity of war. Degaussing is another example. It wouldn't have been developed so quickly, or perhaps even at all, if not for the immense pressure to find a solution. The best minds were mobilized, resources were allocated without normal budgetary constraints, and experimentation was encouraged. When survival is at stake, innovation accelerates. Another lesson is the importance of ordinary people doing extraordinary work. WWII wasn't a famous genius like Einstein or Turing. He was a skilled technician who saw a problem and devised a solution. There are thousands of stories like his from World War II, people whose names have been forgotten but whose contributions were vital. The electricians who installed and maintained degaussing systems, working in dangerous conditions, often under enemy fire. The radio operators who maintained communications despite jamming attempts. The mechanics who kept engines running with improvised spare parts. The cooks who fed crews on limited rations. Each of them played a vital role in the victory. Returning to the Battle of the Atlantic, 1943 marked the turning point. Allied merchant shipping losses fell dramatically, while U-boat losses increased. Several factors contributed to this. More naval escorts were available. Long-range aircraft began to cover the void in the mid-Atlantic, where ships had previously been left without air protection. British intelligence was breaking German codes and could redirect convoys away from U-boat concentrations. And silently, degaussing was doing its job, allowing ships to pass through minefields and reducing the effectiveness of magnetic weapons. In May 1943, Admiral Dönitz temporarily withdrew his U-boats from the North Atlantic. He recognized that the losses had become unsustainable. Of the approximately 1,000 submarines Germany built during the war, approximately 800 were sunk. Of the approximately 40,000 people who served in the German submarine force, about 30,000 died. It was one of the highest mortality rates of any military branch on either side of the war. For those who survived, the experience was traumatic. Living in a cramped metal tube, never knowing when the next depth charge would arrive, breathing stale air, eating spoiled food, watching friends die in horrific explosions. It was a nightmare that many never fully overcame. On the Allied side, victory in the Battle of the Atlantic allowed the buildup of forces for the invasion of Europe. Without control of the sea lanes, D-Day would have been impossible. The millions of tons of equipment, the hundreds of thousands of soldiers, the endless supplies required for an operation of this magnitude, all depended on crossing the Atlantic safely. When the Allied forces landed in Normandy on June 6, 1944, they did so because the sea bridge supporting them was secure. And part of that security came from a cable wrapped around each ship, carrying a chain that created an invisible protective field. After the war, Charles Goodhue continued working on scientific research. He never became a celebrity. There were no parades in his honor, no monuments built. But those who knew his work knew its importance. He received military decorations and recognition from his peers. Most importantly, he had the satisfaction of knowing that his idea saved countless lives. How many exactly, we will never know. How do you count the ships that didn't sink, the lives that weren't lost, the supplies that reached their destination? But it was certainly thousands, perhaps tens of thousands. The history of degaussing reminds us that in war, as in life, the one with the most powerful weapons doesn't always win. Sometimes the one who solves problems most intelligently wins. U-boats were formidable war machines, but they were defeated not just by brute force, but by intelligence, determination, and the creativity of people like Goodhue. World War II was won in factories and laboratories as much as on battlefields. It was won by scientists and engineers as much as by soldiers and sailors. It's also important to recognize the human cost behind these statistics and technologies. Every ship that sank before degaussing was widely implemented, took dozens or hundreds of people with it. Merchant seamen with no military training, simply trying to do their jobs and support their families. Many of them never stood a chance when the torpedoes hit. The icy North Atlantic kills within minutes. Even those who made it into lifeboats often died of hypothermia or dehydration before rescue arrived. Thinking about the agony of those men floating in an empty ocean, knowing death was near, is heartbreaking. Degaussing didn't bring any of them back, but it prevented many others from suffering the same fate. Today, when we see ships on the horizon, We rarely think about the complex engineering that keeps them functioning. We don't see the degaussing cables wrapped around their hulls, still there, still working, still protecting against a threat most people don't even know exists. We don't think about the generators that supply the current, the controls that adjust it, the technicians who keep everything running smoothly. All this complexity is hidden, doing its job silently. It's the same with many of the technologies that protect us. They exist in the shadows, invisible until the moment they fail, and we realize how dependent we were on them. The journey from the degaussing concept to its widespread implementation was not straightforward. There were failures, there were setbacks, and there were times when it seemed it wouldn't work. On some of the first ships equipped, the system caused interference with magnetic compasses, making navigation inaccurate. Engineers had to redesign the installation to minimize this interference. In other cases, the current required for proper degaussing was so high that it overloaded the ship's generators. New generators needed to be installed, or existing systems needed to be reinforced. There were also instances of poorly installed cables coming loose during storms, dragging along the hull and causing damage. Each problem was resolved through trial and error, drawing on the experience gained from hundreds of installations. One aspect worth highlighting is the international cooperation in implementing degaussing. It wasn't just the British who used this technology. Americans, Canadians, and other allied nations quickly adopted the system. There was sharing of technical information, sharing of best practices, and sharing of resources. At a time when survival was at stake, national rivalries were set aside in favor of cooperation. This is a powerful reminder that when humanity faces existential threats, we are capable of working together in extraordinary ways. It would be wonderful if we could do this not only in war, but also in peace. Consider for a moment the audacity of the original idea. WWII was essentially proposing that a simple electrical cable could render a giant warship invisible to magnetic detection. If someone were to propose this today in a corporate meeting without any prior evidence, they would likely be ridiculed. But WWII had the courage to defend his idea, to insist that it was worth testing, to do the hard work necessary to prove it worked. How many other brilliant ideas have been lost because their proponents lacked this courage? How many solutions to current problems are waiting somewhere in the mind of someone who dares not share them for fear of ridicule? There's a mathematical elegance to degaussing that's beautifully simple. If you have a magnetic vector pointing in one direction, all you need to do is create another vector of the same magnitude pointing in the opposite direction, and they cancel each other out. It's basic vector algebra. But applying this mathematical simplicity to the real world, where magnetic fields are three-dimensional, where they vary with position, where multiple factors affect their strength and direction, requires practical genius. It's the difference between knowing the theory and being able to make it work in practice. During the large-scale implementation of degaussing, interesting stories of improvisation and creativity emerged. In a remote port in Canada, where specialized equipment was unavailable, a group of technicians built their own measuring system using ordinary calipers, pieces of wire, and car batteries. It wasn't as accurate as professional instruments, but it worked well enough to calibrate the degaussing of several waiting merchant ships. These ships went to sea and survived their voyages, bringing vital cargo. The improvised solution saved lives as much as the sophisticated technology. There is also the story of an old oil tanker that was scheduled to be retired for being too old and too slow. But the war demanded every available ship. It was fitted with degaussing and returned to service. This tired old tanker ended up making 12 more Atlantic crossings, delivering critical fuel each time. On its last voyage, in 1945, when the war was practically won, it was finally hit by a torpedo from one of the last operational U-boats. But even then, degaussing had done its job for years, allowing that ship to deliver thousands of tons of fuel that helped keep the Allied war machine running. When it sank, it did so having fulfilled its duty far beyond anyone's expectations. German submariners, for their part, developed a grudging respect for Allied ingenuity. In memoirs written after the war, several U-boat commanders recounted the frustration of seeing their magnetic torpedoes repeatedly misfire. They knew they had calculated everything correctly, that they were in the perfect position, that the torpedo should have exploded. But nothing happened. The torpedo would pass under the target and continue until its energy ran out, and it sank uselessly into the ocean. It took time for the Germans to understand that it wasn't the torpedo's fault. It was that the targets had changed their characteristics. When they finally learned about degaussing, some commanders admitted it was a brilliant stroke, exactly the kind of solution they themselves would have admired if they had been on the other side. Submarine warfare in World War II was unlike any other form of combat. There were no clear front lines. There was no territory to conquer or defend. It was a struggle for the ability to move things across the ocean. Whoever controlled the sea lanes controlled the flow of resources, and whoever controlled the resources won the war. It was as simple and as vital as that. U-boats attempted to strangle Britain by cutting off its supply lines. Degaussing was one of many tools that prevented this from happening. It wasn't the only solution, but it was a crucial part of a complex defense system. Another fascinating aspect is how degaussing interacted with other technologies. For example, when the Allies began using radar more widely, ships needed to balance their radar electromagnetic emissions with their degaussing systems. In theory, the two technologies were compatible, but in practice, there was occasional interference. Engineers had to learn how to properly shield the degaussing cables to prevent them from interfering with radar signals. They also had to ensure that the radars themselves did not interfere with the sensors used to monitor degaussing. It was a complex technological puzzle with multiple pieces that needed to work together harmoniously. Maintaining degaussing systems during long voyages was a constant challenge. Imagine being in the middle of the Atlantic, thousands of miles from the nearest port, and your degaussing system failing. You can't simply call a technician or go to a repair shop. The crew has to fix the problem with whatever they have available. This meant that each ship needed to carry spare parts, specialized tools, and most importantly, have at least some crew members trained in electrical repair. Many ordinary sailors learned the basics of naval electricity during the war, not by choice, but by necessity. This forced training proved invaluable to many of them in their civilian lives after the war. With long-term impacts in mind, the development of degaussing contributed to the broader field of electronic warfare. The idea of using electromagnetic fields for both attack and defense has expanded immensely since World War II. Today, we have sophisticated electronic countermeasures that can confuse guided missiles, jam enemy radars, and shield aircraft from detection. All of this has conceptual roots in the pioneering work done with degaussing. The realization that you can manipulate the electromagnetic spectrum to your advantage, that you can become invisible or confuse enemy sensors through clever engineering, was revolutionary. Returning to the human experience, it's worth remembering that for sailors on ships, degaussing was invisible and silent. They couldn't see if it was working. There were no dramatic indicators that they were protected. They had to blindly trust that the cable coiled around the hull, the generator humming somewhere below deck, the technician checking gauges, all were doing their job. It was an act of faith, and for many, that faith was vindicated when their ship passed through mined areas without incident, or when a torpedo that should have destroyed them inexplicably failed. Only then did they realize that something invisible had protected them. There are reports of sailors who, after the war, visited the holds of their old ships and finally saw the degaussing systems. Some were surprised by their simplicity. Just thick cables wrapped around the structure, connected to generators. It didn't look like much, but those simple cables were the difference between life and death. Sometimes the greatest protections are the most humble in appearance. They don't need to be imposing or impressive. They just need to work when needed. The scale of the degaussing operation is staggering when you really think about it. By the end of the war, tens of thousands of ships had been equipped with degaussing systems. This represented hundreds of thousands of kilometers of special cable, thousands of dedicated generators, and countless hours of installation and maintenance work. Coordinating all of this across multiple nations with different standards and practices was a monumental logistical feat. There was an entire bureaucracy dedicated solely to ensuring the degaussing program ran smoothly. Forms needed to be filled out, inspections needed to be scheduled, reports needed to be filed. It wasn't glamorous, but it was necessary. An interesting technical detail is that degaussing wasn't simply turned on and left running at the same intensity all the time. Smart ships adjusted their systems depending on the expected threat. If they were sailing in relatively safe waters, they could reduce degaussing power to save fuel and equipment wear. If they were entering areas known to have magnetic mines or high U-boat activity, they increased power to maximum. This tactical management of degaussing required knowledge of both the strategic situation and the technical capabilities of the system itself. Ship captains needed to work closely with their electrical technicians to make these decisions. There have also been instances where degaussing has saved ships in unexpected ways. One incident involved a British warship being pursued by a German surface unit in shallow waters. The British commander made a risky decision to sail through a narrow channel he knew was mined, betting that his degaussing would protect him. The Germans, who knew the minefield, did not follow him, hoping the mines would do the trick. But the British ship passed through unharmed and escaped. It was a brilliant tactical use of a defensive capability, turning it into a strategic advantage. As the war progressed and the tide turned in the Allies' favor, degaussing remained important even as the U-boat threat diminished. Allied forces began amphibious operations on multiple fronts: North Africa, Sicily, Italy, and finally France. Each of these operations required ships approaching hostile, often mined coasts. Degaussing allowed invasion fleets to approach with minimized losses. It wasn't a perfect guarantee. Mines still sank some ships, but the percentage of losses would have been much higher without degaussing's protection. On the Pacific Front, where naval warfare had a different character, degaussing was also valuable. The Japanese used magnetic mines extensively to protect their coastal waters and bases. As American forces approached Japan through an island-hopping campaign, they encountered these minefields repeatedly. Ships equipped with degaussing could operate more aggressively in contested waters. This gave American commanders greater tactical flexibility, allowing them to risk operations that would have been suicidal without magnetic protection. Interestingly, degaussing also had applications in maintaining strategic surprise. If enemies monitored magnetic activity in certain areas, a sudden increase could signal a buildup of naval forces. With degaussing, fleets could concentrate with reduced magnetic signatures, making detection by long-range surveillance difficult. This was particularly relevant in operations where surprise was critical. The ability to hide not just individual ships, but entire fleets from magnetic detection added another layer of operational security. After the Allied victory in 1945, much of the technology developed during the war was classified and kept secret. Degaussing, however, eventually became public knowledge as its historical significance was recognized. Academic studies were published, documents were declassified, and veterans shared their experiences. Today, the history of degaussing is taught at naval academies around the world as a classic example of practical problem-solving engineering. Naval engineering students learn not only how the system works, but also the broader lessons of innovation under pressure and the importance of elegantly simple solutions. The legacy of Charles Goodeve and other engineers who worked on degaussing extends beyond the specific technology they created. They set a precedent for close collaboration between scientists, engineers, and the military. Before World War II, there was often a separation between academia and the military. The war forced these worlds to work together in unprecedented ways. This collaboration continued after the war and is now standard in many countries. Defense agencies maintain close relationships with universities and research laboratories, recognizing that innovation can come from anywhere. It's also worth mentioning the economic cost of the degaussing program. Amid the massive expenditures of the war, degaussing was relatively inexpensive. The cost of equipping a ship with degaussing was a tiny fraction of the cost of the ship itself and its cargo. The return on this investment was extraordinary. Each ship saved meant not only the preservation of the ship itself, but also of its cargo, crew, and the ability to make more voyages. In purely economic terms, it was one of the most efficient investments made during the entire war. This illustrates an important principle. Protection and prevention are often far cheaper than replacement and recovery. There's a human dimension to this story that can't be overlooked. Behind every statistic, every ship saved, every mine avoided, there are real people. Sailors who returned home to their families because a power line protected them from a mine they'd never seen. Children who grew up with their parents because an electrician had a brilliant idea. Communities that didn't lose their young people in the icy waters of the Atlantic. It's impossible to fully quantify this human impact, but it's there, reverberating through generations. Imagine the family reunions after the war, where veterans could finally talk about their experiences. Some would have recounted the moment they learned they were sailing in mined waters, the fear they felt, and then the inexplicable relief when nothing happened. They didn't know it at the time, but their ship was protected by degaussing. Years later, they might have read about the technology in a book or seen a documentary, and they finally understood why they survived when so many others did not. It must have been a powerful moment of gratitude, not just for being alive, but for the human ingenuity that made it possible. The development of degaussing also teaches us about the nature of innovation itself. Innovation isn't always about creating something completely new from scratch. Sometimes it's about applying existing knowledge in novel ways. The basic principles of electromagnetism were known decades before World War II. What WWII did was see how these principles could be applied to the specific problem of magnetic detection of ships. He connected dots that others hadn't. That's what innovators do. They see possibilities where others see only problems. As we near the end of this story, it's important to reflect on the broader context. World War II was a human catastrophe of unimaginable proportions. Tens of millions of people died. Cities were destroyed. Cultures were devastated. Families were torn apart. No technology, no matter how brilliant, can compensate for this suffering. Degaussing saved lives, yes, but it didn't bring back those already lost. It didn't rebuild destroyed homes. It didn't heal psychological trauma. It's important to celebrate human ingenuity without romanticizing the war that necessitated it. That said, there is value in studying how people responded to the immense challenges they faced. Degaussing is a story about not giving up, about continuing to seek solutions even when the problem seems insurmountable. In 1941 and 1942, when U-boats seemed invincible, it would have been easy to despair. But engineers and scientists kept working, kept testing ideas, kept refining solutions. Their persistence made a difference. This is an example that resonates beyond war, applicable to any difficult challenge we face. In the post-war years, as veterans returned home and society began to rebuild, many of those who worked on projects like degaussing returned to quiet civilian lives. They didn't become celebrated heroes. There were no Hollywood movies about their contributions. But they knew what they had done. They knew their work mattered, and for many, that was enough. There's a quiet nobility in doing important work well, without the need for public recognition. Our society is built by millions of people like this, doing essential work that never makes the headlines. Technology always marches forward. Today's ships are radically different from those of World War II. They are larger, faster, and more efficient. They are built with modern materials and equipped with sophisticated electronics, but they still use degaussing. The technology has been refined, automated, and integrated with other systems, but the basic principle remains the same. A cable carries current, creating a magnetic field that protects the ship. WWII's elegantly simple solution still works 80 years later. This is a testament to its fundamental soundness. Looking to the present and the future, the principles learned from degaussing remain relevant. We live in an era of increasingly sophisticated electromagnetic warfare. Drones are detected by their electronic signals. Aircraft are tracked by radar. Submarines are found by acoustic and magnetic signatures. In each case, there is a race between detection and concealment, between attack and defense. Degaussing was an early example of this race. The lessons learned then about how to think about electromagnetic fields, how to manipulate them for tactical advantage, still inform the development of modern military systems. But beyond military applications, there are more universal lessons. The history of degaussing teaches us that complex problems sometimes have surprisingly straightforward solutions. It teaches us that it pays to listen to ideas from unexpected sources. It teaches us that testing and iteration are crucial to turning concepts into reality. It teaches us that collaboration between different types of expertise produces better results than working in isolation. And it teaches us that in times of great pressure, humans are capable of extraordinary creativity and determination. These are lessons that transcend war and technology, applicable to any challenging human endeavor. Looking back through the decades to those dark days of the early 1940s, it's easy for us, with the benefit of historical perspective, to see the turning points and understand why things happened as they did. But for those living through those events, the future was uncertain and frightening. They didn't know they would prevail. They didn't know their innovations would make a difference. They just kept working day after day, doing the best they could with what they had. And collectively, these countless individual actions added up to change the course of history. It's a powerful reminder that our actions matter, even when we can't see their full effects. And so we come to the end of this journey through one of the lesser-known but most important stories of World War II. An electrician had an idea about magnetic fields. He turned that idea into reality despite initial skepticism. His invention was adopted and implemented on a massive scale. It saved countless ships and countless lives. It contributed significantly to the Allied victory in the Battle of the Atlantic, and it established principles that remain relevant today. It is a story of human genius triumphing over adversity, of persistence overcoming doubt, of simplicity resolving complexity. May we learn from examples like this. May we have the courage to propose unconventional ideas. May we have the wisdom to listen to these ideas with an open mind. May we have the determination to test and refine until they work. And may we have the humility to recognize that great solutions can come from unexpected places and people. The electrician's crazy trick worked because he had the audacity to imagine it could work and the ability to make it happen. We can all aspire to this kind of courageous and innovative thinking in our own lives, in our own challenges. May the Lord God bless those who used their minds and hands to protect lives in times of great danger, and may He continue to inspire us with wisdom and courage to face the challenges of our own time with the same determination and creativity.